Assalamu alaikum and hello everyone. In this fourth video, we are going to study homogeneous differential equations of the first order. These equations are very important because even if they don't look simple at first, we can transform them into separable equations using a clever change of variables. First, let's define what homogeneous equations is. Consider the general form y prime equals f of x and y. We say this equation is homogeneous if the function f is a homogeneous function of degree 0. This means that if you replace x with kx and y by ky, the constants k cancel out and the function doesn't change. I can write it like this. And here we can always rewrite f as a function of the ratio y over x. For example, g of y over x. To understand this, let's look at an example to verify this property. Consider the equation y prime equals x squared minus y squared over x times y. This is our function f of x and y. If we replace x by kx and y by ky, we obtain this. Then by factoring k squared in the numerator and the denominator, we obtain k squared times x squared minus y squared over k squared times x times y. As you can see, k squared cancels out perfectly. We are left with our original function f of x and y. So this equation is indeed homogeneous. As I told you before, we can write now this equation in this form. And now we can write it as a function of the ratio y over x. To solve these equations, we use a specific substitution, which is y equals yx, or you can find it in this form. If we assume y is the product, then its derivative, y prime, must follow the product rule, and we obtain x times y prime plus, by plugging this in our equation, we transform it into a separable variable equation that we already know how to solve. First, we write it in terms of u and x. Y prime is replaced by x u prime plus u, and the ratio y over x is replaced by u. Next, we isolate the derivative. Let's move u to the other side. To simplify, we put everything over the same denominator. Now we move the u terms to the left and x terms to the right. Don't forget that u prime is equals to du over dx. Now we only have to integrate the both sides. And we obtain this. Finally, we replace u by y over x. Which is our solution in an implicit form. Let's move to another case. Sometimes equations appears as a fraction of two linear functions, like this. And we have three different cases. The first one is when C1 and C2 are equals to 0. By dividing by x, we obtain this. And as you can see, this is a standard homogeneous equation. And we proceed just like the previous example by putting u equals y over x. Now, the case 2, which is the parallel case, if the two lines are parallel, we are going to use a specific substitution. For instance, to see if the lines are parallel, we only have to calculate the determinant of this matrix. And if this determinant is equal to 0, we use the substitution u equals a1x plus b1y. Let's see an example for this case. If we have the equation dy over dx equals x plus 2y plus 1 over dx plus 4y plus 3. Without calculating the determinant, we can write the equation like this to see that the two lines are parallel. If we calculate the determinant of the matrix 1, 2, 2, 4, which is 1 times 4 minus 2 times 2, which is 0, you can conclude that the lines are parallel. So now we are going to use the substitution u equals x plus 2y, then u prime equals 1 plus 2y prime. Then y prime equals u prime minus 1 over 2. Now we substitute this in our equation, and this here, and this here, and here. Our equation becomes u prime minus 1 over 2 equals u plus 1 over 2u plus 3, which is a separable equation. To see this, let's put the u terms in one side and the x terms in the other side. First, let me write this. We multiply by 2. Then we add 1. We write the same denominator on the right side. To obtain 4u plus 5 over du plus 3. Now we separate the variables. I must add another page, sorry. Now we integrate the both sides. To facilitate the integration, I have to change the form of the left term. Let me multiply everything by 2. Then by the Euclidean division, we obtain this. And here the antiderivative is very easy. We return to our substitution, which is u equals x plus 2y. And this is our solution in an implicit form. Now let's move to another case. We talk about this form of equations. The case number 3 is when the determinant of this matrix is not equal to 0, which means that the lines are not parallel. So we use a translation of the variables, which is x equals big X plus alpha and small y equals big Y plus beta, to remove the constants C1 and C2, and leaving us with a homogeneous equation in big X and big Y. Let's see a practical example. I am going to use this example. As you can see, the determinant of the matrix equals minus 1, and it is equals to minus 2, not equal to 0, then the lines are not parallel. We are going to put x and y equals big X plus alpha and big Y plus beta. We replace this in our equation, obtain dy over dx equals to big X plus alpha plus big Y plus beta minus 3 over big X plus alpha minus big Y minus beta minus 1. Now we are going to solve a system to cancel this. First, let's write our system. To find alpha and beta, I am going to summing the two equations. Here I get alpha equals 2. We only have to replace this here to obtain beta equals 1. We return to our equation. Here dy over dx becomes x plus y over x minus big Y. Don't forget that what is in the yellow color is equal to 0. By dividing by x, we obtain this, which is an homogeneous equation that we now have to solve by putting u equals y over x, or big Y equals x times y, then y prime equals u prime times x plus y. We replace this here, and u instead of y over x, our equation becomes becomes like this. Now we have to separate the variables. First, we add minus u. We put this with the same denominator, u minus u plus u squared. Then we put the u terms, sorry, I have to add another page. We put the u terms in one side and the x terms in the other side, like this. To integrate the both sides, first let's write the left term in this form to make it easy for later. Now we integrate to obtain the arctangent of u minus 1 over 2 the logarithm of 1 plus u squared equals the logarithm of x plus c. Now we have to return to our variables small x and small y. I have to return here. First we have u equals big Y over big X, and we have to return to this translation with alpha and beta equals to 2 and 1. Sorry. Uh, Then here big X equals small x minus alpha with alpha equals to 2, and big Y equals to small y minus beta with beta equals 1. Then we replace this here. Then we must write instead of u y minus 1 over x minus 2. Let's move this here. And now we can write our general solution of our equation in an implicit form like this: minus 2 minus 1 over 2, the logarithm of 1 plus y minus 1 x over 2 squared equals to the logarithm of x, and x here is small x minus 2 plus c. It is a big solution. Okay. To summarize, homogeneous equations can be solved by reducing them to separable ones using the right substitution. Keep in mind that the goal is always the same: simplify the equation. In the next video, we will move on to exact equations. See you in the next video, and bye.